discussed observation this morning. And a lot of, when you see these various talks, meetings like this, a lot of the new ideas that are introduced are often motivated by this problem. And I think it's very important then to understand what this problem really is. What you're often told is that the cosmological constant problem is one of the following. Why is the cosmological constant not Planck mass to the fourth? Why is the cosmological constant not 0? Why is it 10 to the minus 120 times the Planck mass to the fourth? But these ways of stating the cosmological constant, well, for want of a better way of saying it, they're all nonsense. None of those are really what the true nature of the cosmological constant problem is. And the reason really boils down to trying to understand the nature of the problem. I mean, the cosmological constant problem, when it was first formulated, was really a problem associated with effective field theory. And an object like the cosmological constant, quite simply within the context of effective field theories, like the standard model, coupled to gravity, is not something that you can actually predict. You cannot predict the cosmological constant within the language of effective field theory. So why are we fretting about all these questions, posed as they are? The cosmological constant is something that we can't predict it, so we should just measure it. And that's what I want to emphasize. But of course, once you've measured it, if you can measure it, I'll ask about that in a minute. Once you've measured it, you then have to answer the question, well, is that measurement robust against radiative corrections? And that is the true nature of the cosmological constant problem, because as far as our understanding it is concerned, it is not. So the real key to solving the problem is to find a way to make the cosmological constant stable against radiative corrections. Okay? If you do a one-off fine-tuning, that's fine, but once you've done that, and then you go away and measure it, that measurement must be stable against radiative corrections in your effective field theory description. Okay, so I've emphasized there about the role of measuring the cosmological constant. And that's a very important thing, and this is what this sort of first slide is supposed to depict. It's supposed to, well, Atlas holding up the world, but you can think of the cosmological constant as being, trying to measure it as being sort of weighing the entire universe. And that statement, the entire universe, is absolutely crucial here. Because if you think about how you actually measure the cosmological constant, think about what you actually have to do. To be sure that the thing that you're measuring, the thing that you're interested in, truly is the cosmological constant, the true zero-point energy of the universe, you have to scan all of space and all of time. And the reason that is because you need to be sure that what you're talking about is not some sort of potential that looks very flat, say in this room, but dies off at very large distances or at very late times. You need to be sure that what you're talking about is truly constant on the scale of the entire universe. And the reason for this is because the cosmological constant is truly the global component of the energy momentum tensor. So if we really need to scan all of space and all of time, we really need to look at the universe on a global level to even measure the cosmological constant. Then if we're going to try and deal with its radiative corrections, surely we should really be thinking about things on that level, on a global level. And that's what I really want to emphasize in the second part of my talk. I want to emphasize, if we're going to say modify gravity, which is something that's very fashionable, to try and attack this problem, that we should be modifying gravity on a global level. That's the key message that I want to get across. And I'm going to give you an example of a way of doing that achieves what we hope to achieve. And this is work that I've been doing with the manual caliper. And it really is, we've called it the sequester. And the idea is that we modify gravity globally. Locally, our theory is identical to general relativity, so we do not have to jump through any hoops or any screening mechanisms, none of that, to try and make sure that we recover the great successes of general relativity in the solar system. We don't have to do any of that. It just comes to the ride. The modification is on a global level. And that's okay, because the thing you're trying to deal with is really a global thing. Okay? So I should also say that whilst I'll be presenting in the second part of the talk a specific model that does this, it's really, as we've come to realise now, although we haven't published it, it's really one of a scheme, just one part of an entire scheme of these ways of modifying gravity on a global level to try and swallow up those radiative corrections to the cosmological constant. But you'll see it as the talk goes on. Okay, so this idea is really sort of stems from 3 papers now. There's plenty more in the pipeline of work that I've been doing with the Manu Caliper over the past year. The Manu came to Nottingham as a Labour Hume visiting professor, and it's been a very fruitful collaboration. So, okay, so let me begin by describing the cosmological constant problem and its true nature. Well, one thing we know about the cosmological constant problem is that it's hard. Okay, but if we're going to try and attack something that is that hard, then we better first think about trying to understand what the problem really is. And as I said, it's not going to be those things that I said at the start. So what the problem really brings together are sort of 2 of the great triumphs of 20th century physics. So essentially, on the one hand, you've got quantum field theory, locality, unitarity, all that. And on the other hand, you have general relativity with things like general coordinate variance and the equivalence principle, the key elements of it. And those 2 sort of great cornerstones of modern physics, when you bring them together, you end up with the cosmological constant problem. And the reason for that, quantum field theory on the one hand tells you that you have vacuum energy. Unitarity requires that it release vacuum loops. And then the equivalence principle tells you that just like any other form of energy, they gravitate. Okay? And general covariance tells you how they gravitate, because the measure now has to become a covariant measure. So when you vary it with respect to the metric, you get a contribution to the energy momentum tensor. This is all given to you just from these very sort of minimal principles, if you like. But of course, this isn't the full story, because you're always free to add a bare cosmological constant to the action, so you do that. And so it's the combination of this vacuum energy contribution and the bare contribution that actually gravitates. So that's the thing that you constrain, if you like. Okay, so you have this total contribution coming from vacuum energy and the bare value. An observation, in inverted commas here, because I've just talked about how you measure the cosmological constant and the ambiguities in that. But observation tells you that this should not exceed a milli-electron volts to the 4th, which is, of course, the dark energy scale. Okay, so how do you estimate this contribution coming from the vacuum energy? Well, there's the kind of sort of Babe way to do it, if you like, which is you treat every particle as a harmonic oscillator, and you sum up the 0-point energy contributions. And what you find when you do that is that each particle up to the cutoff contributes its mass to the 4th. And already with the electron, that's way too big a contribution. Okay? There is a sort of slightly more grown-up way of thinking about this, and actually you start calculating loops. So you take a loop of some field here. The example here is just a scalar field in that sense, an illustrative example, and you attach it to an external graviton. Okay, and you only have to calculate the one diagram because general covariance tells you the overall structure. And you calculate this, and you get the following expression using here I've used dimensional regularization when you calculate this loop. And you see that it is scaling like the mass to the 4th, just like the other calculation. Of course, there are a few other elements of this that we need to think about. And this is important. There's divergent piece, of course there is. Okay, as you'd expect. And actually, this sort of almost makes a mockery of some of these fine-tuning statements. Because this problem is only really well formulated within the language, like I say, of effective field theory, and even perturbation theory is the only thing I really know how to do here. And then as soon as you start doing loops with perturbation theory, you know you get these divergences. And so you just cancel them off. That's free normalization. Okay? So why are we fretting about these cancellations of order 10 to the 120 when we're cancelling off divergences before we even got there? So what is the cosmological constant problem not? Well, I guess you're sort of going to guess now. It's not the question of why the cosmological constant is so small. It's not this picture that you often see, where you talk about the electron contribution as being a mega electron volt to the fourth, that being requiring you to fine-tune the finite part of the cosmological constant to 36 decimal places, and then the situation gets worse and worse and worse as you go up in scale. It's not really that problem. Okay. So let's think a little bit more about what the problem actually is. The truth. So like I said, so you have this contribution to vacuum energy coming from this loop calculation. Just done a one loop here. Okay. You've got this divergent part, and like, as soon as you get this divergent part, you know you need to add a counter term to cancel it off, so you use your counter terms to do that cancellation. And in doing so, you introduce an arbitrary subtraction scale, which is this curly arrow. You combine the two, and you get your renormalized vacuum energy. No divergence now. Indeed, it goes like mass to the fourth. But you've also got this arbitrary subtraction scale in there. And what that means is, what that's telling you, is that you cannot predict the value of this cosmological constant, not within the language of effective field theory that we're using here. So if you can't predict it, what else have you got to do? Well, you just measure it. That's what you do in these scenarios. So you just measure it. So stop fretting about trying to predict it. Until you know the full theory of everything, even if such a theory exists, there's no way you can predict it. You just measure it. Big, small, who cares? Just measure it. Turns out to be small, that's fine. But then you have to have, the thing is, you still have a problem now, and this is the true nature of the cosmological constant problem. So you've measured it, it's small. How do you measure it? Well, as I emphasized earlier, to truly measure the cosmological constant, you have to scan the whole of space and the whole of time. So I think it's an important point. You can't measure the cosmological constant in this room, because you don't know that what you're talking about is not just some potential whose value is going to change when you go out of this room. And this applies temporally as well. Okay? So you truly have to go below them to measure the cosmological constant. So that's how you measure it. So what is the problem? What's the issue here? Well, it's really one of radiative instability. Okay, this is the true nature of the problem. And I'm going to describe it now in the context of the one thing that I know how to do, which is with effective field theory and perturbation theory. You can describe it in other ways too, but I'm not going to do that. So here's the radiative instability. So you calculate your one loop contribution. Okay. You've subtracted off the divergent parts. And you focus on the finite part. And you get something that goes like roughly like the cutoff to the fourth power. So let's say you have supersymmetry above a TV. This might be about TV to the fourth. And then you need to tune to match observation now, which because you measured this guy, right? Now, to match observation, you need to tune this lambda vertic rate to precision. Okay, that's fine. That's actually fine by itself. So one-off fine-tuning, that's okay. The trouble is that then you do that, and then you ask somebody changes the effective description, so you go to a two-loop description. Okay, fine. You do your two-loop calculation. You calculate the two-loop correction, and you see it's pretty much, because standard model couplings are about 10, it's pretty much in the same order. So you need to completely retune your bare parameter to the same degree of precision. Okay? But then you have to do it again, at 3 loops, and 4 loops, and 5, and so on and so forth. It's a completely unstable process. As soon as you retune, you change the description, you have to retune again. This is not how we like vector field theories to work. Now you might say, why don't I just sum up all the loops, stop fretting about this? Okay, but in what theory? To generally have control over that statement, you really need to know the full theory, all the way up. What we're working with here is vector field theory. Now you can describe that sort of lack of knowledge of what's going on in the UV using sort of Wilsonian methods, but the problem still occurs. Just takes a slightly different guide. But it all boils down to trying to keep control over these radiative corrections. If it's beyond some certain order you can keep control of them, then you're fine. Okay? We can't. As it stands. So this is the mission. The mission is to try to make the cosmological constant radiatively stable. So what I'm going to try and propose here is a way of doing that in which you do it at the level of the standard model loops. I'm not going to deal with graviton loops. But that's all that's where the problem really arises in the first place. So how are you going to think about doing that? Well, you're not going to try to make those radiative corrections small. We're not asking why the radiative corrections are small. We're going to try to stop them gravitating. That's the philosophy. So the radiative corrections are going to be there, but for some reason, they do not gravitate. That's all you need. But then you run into this no-go area of Weinberg's. Can you really do this? Weinberg has this famous no-go theorem that says, you want some sort of self-adjustment mechanism whereby you add extra fields whose role it is to swallow up the cosmological constant. You simply can't do that. Okay? So any model that does this has to try to get around Weinberg's no-go theorem. And one thing that Weinberg's no-go theorem applies to is local theories. Okay? And what we're going to do, inspired by understanding how you can measure the cosmological constant, which is at this global level, we're going to modify gravity globally. So we're not going to be pinned down by Weinberg. Okay, so this brings us to the sequester. So the idea here is to go global, as I've emphasized. We're going to modify general relativity globally. And like I say, I should emphasize that what I'm going to propose is just it is now a scheme, I think. It's now a paradigm, if you like. We're not talking about, I will present a specific model, but you should understand that this is a way of doing things that we haven't really thought of before. Okay. There are generalizations of the model which we haven't put out yet. Okay, so here's my starting point. Now, I'm sure you'll all recognize this action. It is, of course, the action just for general relativity with some bare cosmological constant lambda and matter minimally coupled to some metric g. This is the matter Lagrangian here. Okay, great. So obviously that's not quite the theory, because this would obviously suffer from the cosmological constant problem. But it's pretty close to what I'm going to propose. Okay, so what am I going to do? The first thing I want to do is so the red doesn't show up very well, but I want to promote that bare cosmological constant to something that's dynamical. I'm not going to make it something that varies in space and time, nothing like that. It's still a global quantity. It's still constant in space and time, but it's dynamical. So in principle I can vary over it. Okay? By making it dynamical, dynamics can make it take on a particular value, and that's going to be the idea. So that's the bare cosmological constant. The other thing that plays a role in this game is what the matter sector is doing. So I'm going to introduce a second dynamical variable, which I call little lambda, which somehow knows about the scales in the matter sector. In fact, little lambda is introduced in such a way that if you have some bare mass parameter in the matter Lagrangian, then what lambda does is just rescales it to give you the physical mass. Okay? So lambda is effectively setting the hierarchy between the physical masses coming from the matter sector and the Planck mass. I'm not suggesting I'm solving any hierarchy problem here, but this is what lambda does. Okay, so these are your, so you're going to vary over these two guys, but they need to talk to each other, because in the end we want one to cancel off a contribution from the other. So we add a piece to get them to talk to each other, whose form is essentially just fixed by dimensional analysis. So what I have here is this sigma. This depends on the global variables. There's some mass scale mu. Details of that don't really matter. Okay, this guy's not integrated over. Of course it's not, because the fields inside here are not local. These are global. Okay, this is something different to how you normally think about things. Okay, but if you want to think, say, about path integrals, you can imagine that there's, as well as the sort of the functional integration over the metric, say, and the matter fields, there's also like an ordinary integration over these global guys. And so just using the method of steepest descent, you stationary phase, you get equations of motion for these global guys as well. So what are they? Well, here they are. The global equations of motion obviously, of course, give you the variation of the global guys obviously give you global equations of motion. Okay, and you also get the standard Einstein equation, with a contribution coming from the bare cosmological constant and also the matter sector. Okay, here you see that lambda to the 4 appearing because, of course, the matter sector is the dimension 4 guy, and lambda rescales the masses. Okay, so what I want to do is now is the first two equations, you can see that if I combine them, I can actually get a value for what this bare cosmological constant is. In general relativity, that's a completely arbitrary thing. You don't know what it is. You just have to fix it. You tune it. Here it's actually given to me by the dynamics. And what does it give me? Well, it tells me that lambda should be the space-time average of the trace of the energy momentum tensor. Okay? It's a space-time average. Of course, we shouldn't be surprised that such things are appearing because we've modified gravity on a global level. I should also emphasize that there's no issue with causality here, as you might think. Okay? We haven't messed with causality on a local level. There are no local pathologies that you might associate with that kind of thing. There are no closed time-like curves, none of that. Okay? Everything here is happening globally. Okay, so you plug that value that you've extracted for the cosmological constant, or the bare value, back into your field equation, and you get the following. And you see this has a beautiful structure, because now you think about what does vacuum energy do. So you take your energy momentum tensor, and you split it up into your vacuum energy contributions and excitations about the vacuum. Now, it doesn't matter what's the effective description I have for my matter Lagrangian now. Okay, whether I work for 1 loop, 2 loops, 3 loops, whatever, with some particular cutoff, it doesn't matter. Okay, that might affect the precise value of this V back, but it's not going to matter. And the reason is, when I plug this back into the equation, this V back drops out completely. And why does it do that? Because we've zoomed in on its key feature. And the key feature of this guy is that it is constant, truly constant. So it essentially doesn't see this averaging procedure. And so the contribution you get back is precisely the right amount to get the cancellation you need. So when you plug it back in, you see that you just see the excitation. Okay, so the radiative instability is gone. And that's the power of this approach. So the vacuum energy is dropped out in each and every order in perturbation theory. Okay? It's independent. The fact it drops out is independent of where you put your cutoff in your theory. It just drops out. And this might seem reminiscent of unimodular gravity, something like that, but it is not the same. In unimodular gravity, there are hidden equations. Okay? So unimodular gravity, for those who don't know, it's where you just take the traceable part of the Einstein equations. Okay, and there it would seem the vacuum energy is also dropping out, but of course, the problem there is if you take the gradient and integrate up, the vacuum energy comes, the integration, lambda comes back as an integration constant. Okay? So there are no hidden equations here. This is everything. This is absolutely everything. But you do have a residual cosmological constant. That first term there is constant in space-time. It's a space-time average, but it's constant in space-time. So you have this residual cosmological constant left over. It's got nothing to do with vacuum energy. It knows about the excitations. But it is radiatively stable, and so in principle we can fix it empirically. Now, of course it's going to be fixed to be small. It's compatible, our universe is compatible with it being small. And you might say there's some precognition going on there. And I've used that word precognition because that's the word that Coleman used when he first discussed the cosmological constant problem in his wormhole analysis. And I think when you really realise the nature of what the cosmological constant problem is, it's fair enough to have this. But all that's really happening here is one number is being fixed. Like I say, there are no closed time-like curves, none of that. None of these pathologies would often associate with a local violation of causality, because there is no local violation of causality here. There's just one number that the universe knows about at the beginning, and it knows it so that the universe can grow large. So how big is this lambda effective? Well, you can estimate it. And it turns out that those integrals that we're talking about, I mean, it's not obvious, but you can show it, that they're dominated by the values nearest to when the universe is at its largest. And what I'm going to tell you in a minute is that in these universes, the universe has to increase, but eventually will start to crush. So there's some maximum size of the universe in this model, and these integrals will take the values around that scale. So this trace of the energy momentum tensor, this average, will be roughly the energy density of the universe at its maximum size, which is of course less than the energy density today. So this lambda effective is less than the dark energy scale. So this cannot be dark energy. It's too small. But that's not a bad thing necessarily, right? So what are the key observational consequences of such a scenario? Well, they're quite depressing. This is the end of the universe. I've just said that one of the things we predict is that the universe will end in a crunch. Why is that? Well, it's because it has to have finite space-time volume. So one of the equations, I think it's the big lambda equation, relates the space-time volume to some of the other parameters. Now, the form of sigma is not important here, but if you just imagine it's constant for simplicity, just for illustrative purposes, you can see that if the space-time volume is going to grow infinite for fixed mass scale mu, that's going to force lambda to go to 0. And remember what little lambda was. Little lambda was the thing that set the scales in the matter sector. So if little lambda is going to 0, that is forcing your physical particle masses to 0. And that's obviously not our universe. Okay? This is, if you like, conformal limit. Okay, so that's not our universe. So to regulate that, we have to say that the universe has finite space-time volume. But that gives us a concrete prediction. The universe is going to end in a crunch. In particular, that means that dark energy can't last forever. W minus 1 has to be a transient phase. And also, although this isn't immediately obvious just from this simple discussion, we're also going to have a closed universe. So it's going to be less than 0, actually. We need a spatially closed universe. So the things you might be looking for are things like circles in the sky, for evidence of this. Also, possible correlation between the equation of state for dark energy and the curvature. And indeed, we've just seen that there is that. I'll come to that in a moment. Okay, so dark energy can't last forever. So what we've just discovered is that one can propose a minimal scenario where the thing that brings out the cosmological collapse is precisely the thing that is also dark energy. A very minimal scenario. So what kind of thing would bring about cosmological collapse and give you dark energy? Well, the very thing that does that is the very first quintessence potential, written down by Linda, which is, of course, the linear potential. It's linear, so when it rolls to negative values, it gives the necessary negative energy density to collapse the universe. But it also gives you quintessence. And it's also a beautiful potential, as far as quintessence potential goes, because it's protected. It's protected, its form, for example, is protected by shift symmetry. Now, in general relativity, that shift symmetry is actually only pseudo-symmetry. You shift the scalar by a constant amount, and you can compensate that by shifting the cosmological constant. For us, it's an exact symmetry, because we can absorb those shifts in the cosmological constant. The size of the coefficient here is also protected. So this is from matrix of correction. So this is a very elegant potential, very natural. And what you find is that eventually the scalar will dominate because cosmological collapse will always occur. If the scalar is big enough, if it's larger than Planck scale, at the point it starts to dominate, then it will do so in slow roll. This is true even in general relativity. And it does so until it collapses, until collapse kicks in. Yep. But the point is, what's going on there? The collapse time isn't relatively stable. Can I choose it in a relatively stable way? And the issue is you can choose when the collapse occurs in a relatively stable way. So you can just measure it and then that measurement is relatively stable. That's because that coefficient of the potential is relatively stable. What about the initial value of phi once the scalar starts to dominate? Can you choose that in a relatively stable way? In general relativity, you cannot. Okay? For us, you can, thanks to the shift symmetry. But actually, it's even better than that. The sequestering scenario gives you an additional constraint. And it turns out that that constraint is precisely the right thing that picks out the initial value of phi, so that you precisely get slow roll just before collapse. So it's given. So in the sequestering scenario, you're guaranteed to collapse, and you're guaranteed to get a period of dark energy just before that. So why now? Why now? Because the end is nigh. Because collapse is about to occur. Why is it nigh? Because there was a relatively stable parameter, relatively stable being the key point here, that took on some particular value. And we also have a prediction from this scenario. This is a bit out of date now. What we're really predicting here is that 1 plus omega, which is the dark energy equation in state, actually goes like the omega k squared. So we're actually trying to pin that down a bit more precisely with data in collaboration with Adam Moss and Jonathan Pearson. Okay, so there's a bunch of stuff I haven't got time to talk about. I won't go into it now. Time is pretty much up. Of course, there is a symmetry associated with this cancellation mechanism, as you might expect. There are a couple of non-issues I want to touch on. You might talk about the fine-tuning of lambda effective. against observation. It's not really fine-tuning. The main point, of course, is that loops are gone. We've dealt with the relative instability. This issue of acausality, is there some acausality here? Because you're doing these space-time integrals. Well, that was kind of essential. Treating cosmological constants global level, scanning the whole of space and time, was essential in the first place. This was emphasized not by us in the beginning, but by people like Nima, Akani, Hamid, Thermopolis, people like that. But the thing is, we've done this, we've embraced this in the most minimal way. All we've done is we've fixed one number, this lambda effect. And all those horrible loops have been dealt with by the cancellation mechanism. And there are no local pathologies associated with fixing this number. So just to summarize then, what we've done is we've found a way to cancel the standard model vacuum energy contributions at each and every order in loops. And locally we've ended up with a theory which just looks like general relativity with a small cosmological constant. This small value is relatively stable, so we're allowed to fix it empirically. And that essentially sets a global boundary condition. And the main prediction of this, because locally everything just looks like general relativity, the main prediction is that the global one, that the universe is doomed. So I'll stop there.
You earlier talked very much, but could you go back to slide 34?
Okay. Which one's slide 34? Do you know what was on slide?
So you give your equations. So you give
Okay, right.
Yeah.
These ones, or?
Go down one. Go down another one. Yeah, yeah.
Yeah?
The problem with that equation, G mu nu is an Einstein tensor, right?
Yeah.
Okay, the problem with that equation is trace-free on the right and it's not trace-free on the left, so it's generically incompatible.
No, it's not trace-free. This is not the average of this is the space-time motion. This is just a constant. So what is true is if I take the trace and the average, I get that the space-time average of the Ricci scalar is 0.
Which will not be true for most forms of matter.
Ah, no. So that's not true. I mean, it's okay. So here's how you can find solutions to this theory, for example. So you take general relativity with some value of lambda. You don't set it. Okay, so you take general relativity with matter and some value of lambda. Okay. Now, what the sequestering scenario does is it picks out precisely that solution of general relativity of the large class of general relativity solution, which has that the space-time average of R is 0, and it chooses the lambda that does that. So that's the point. So it's this guy that allows you to find the solution.
Right. Tony, I also thought it was a fantastic talk, sort of nice fresh view on the cosmological constant problem. It kind of looks so amazing, it almost must be right. But I didn't understand where that linear quintessence comes in. You don't actually need that.
Okay, so you don't need it for the cancellation mechanism. It's just we wanted to. Okay, so we want a prediction, right? So one of the sort of triumphs of the model, but also a problem of the model, is that it locally just gives you general relativity. So it's hard to get the observers interested. But we do need something. The one prediction we do have is that we need to bring about cosmological collapse. So there are ways to do that, and one way, and we also need the dark energy. We know we need that, and so we thought, well, we can do this in a very minimal way with this linear potential. And so we just looked into that, and then it has this beautiful property that it very naturally gives you dark energy just prior to the collapse, and in a way that won't happen in general relativity without fine-tuning. For us, it comes as part of precisely this constraint of the average of the trace is 0. So yeah, I mean, you can play with all the other dark energy quintessence type models. Absolutely.
David? So how nigh is the end?
Well, the fact that dark energy is around might, if this scenario is correct, suggest not that far. Okay, so we'll try to come up with a date for you once we finish the more sophisticated data analysis with my data colleagues.
have you got a prediction of A of T?
No, not yet. We're working on that. This is so we've teamed up with people who know data better than us to try and pin that down.
Let me question a few of your arguments. You say you work within effective field theory because that's all you know how to do.
That's all the cosmological concepts being
in
properly
effective
formulated.
field theory, you immediately find that your loops are dominated by your ultraviolet cutoff for the region here. That's exactly where effective field theory fails. So, you know, it's perhaps not the best idea to link yourself to effective field theory. Now,
But I can deal with those things.
Let me just go on. Now comes this question of fine-tuning in all orders of magnitude. You can do it in perturbation theory. It simply tells you perturbation theory is not well convergent. If you would compute critical physics and statistical physics by this type of method, you would say there is never any scaling relation because you are missing fixed points. So I think one really has to keep these things in mind. And in addition, what we really observe at the end is just the ratio of cosmological constant divided by the fourth power of Planck mass. So there are many possibilities that the Planck mass, for example, increases and that the cosmological constant at the end just plays no role. I think it's a bit restrictive what you are doing.
Well, what I will say is that okay, so firstly, you do not know, to do the kinds of things that you're thinking of, you need to know what the full theory is. We don't even know that such a thing even exists. But what I can do is I can do effective field theory and I can do perturbation. And actually, even at that level, you have, as you rightly say, an issue with the cosmological constant problem. And that's the only problem that's the only problem I can properly formulate, so that's the one that I'm going to try and solve.
One very short question over there.
Yeah, I just have a question. You mentioned,
Louder, please. Louder.
I have a question. You mentioned unimodular gravity.
Yeah.
Sort of poo-pooed it.
Okay.
Now, if I take ordinary GR, I can always factor it into a unimodular gravity plus the conformal factor.
Okay.
And we know the conformal factor is 6 anyway, because from a field theory perspective, it's a phantom. So, is that related to?
No, it's not really related to the, I mean, to what I'm trying to do here. Yeah, I mean, unimodular gravity, as far as the cosmological constant problem is concerned, I think the view that it doesn't solve it.
I'm not saying it solves it. I'm saying the problem is there in general relativity itself, because you can always affect that factorization. You can
Yeah, I mean,
always
the issue
general
you're talking about the
relativity
conformal
into
ghost.
unimodular plus conformal.
You're talking about the conformal ghost, is that what you're referring to? Yeah, I mean, that's a problem with general relativity, and it would be an issue here. I'm not trying to do anything with, trying to understand quantum gravity in any way here, so whatever solves that for GR will solve it for.
Very short question by Ruth and then the other one.
I have a question a little bit related to Christoph's. If you say you get terms at each order in perturbation theory which are the same order, that's what usually people say when they say it's not relatively stable. Isn't that just a problem of perturbation theory, but not of the cosmological constant?
Well, I think this is the same question.
The problem of the cosmological constant, I would rather formulate it that its value actually changes when you go through a phase transition, and it changes by huge amounts.
Okay, so I think your first point is essentially just answering Christoph's point. So I don't want to repeat, but the issue of phase transitions, okay, well, I can discuss phase transitions. Have I got time? Phase transition is not a problem in this scenario.
I agree you don't know the basic underlying theory, but if there is a problem with perturbation theory.
Well, yes, you can formulate this question using Wilsonian effective field theory methods, and this would still cure the problem as described there.
Are you going
We said that.
to the trip?
Yeah.
You're going to the trip. I think we have to move to the next topic.
The phase transition is
Next topic. The last lecture of this morning session is given by Moodley. We will talk about that set of cosmology with C and E.
Thanks to the organizers for inviting me.
as a probe of the dark sector, but really I was too ambitious there. I'm mostly going to focus on dark energy and the microwave background and galaxy clusters detected using microwaves, so using the Padilla or low-wage effect. So I'm at the University of KwaZulu-Natal. Okay, so I guess this meeting is about the dark universe, talking about dark energy, dark matter. There's also the dark ages, we have dark baryons, missing baryons, so lots of the universe is dark. I'm mostly going to focus on dark energy, as I mentioned in my first slide. And the idea is that the CMB lights up this dark universe. So, while we've learned a lot from the microwave background about the global properties of the universe and the early universe itself, we can use the microwave background as a backlight to basically light up the intervening matter. And to do that, you need to go to small angular scales. And in doing so, you have interaction of the microwave photons with the intervening matter, either through scattering or gravitational processes. Okay, so the microwave background has kind of set the cosmological model. It constrains the global parameters extremely well. So the previous slide was an image from Planck. So this is kind of an internal linear combination. And if you're not using that map, but using the boundary frequency maps and isolating the CMB, removing foregrounds, you can basically get power spectrum. Right, so this is the angular power spectrum. So this is quite recent from last year. And you can use this power spectrum to measure cosmological parameters. In particular, we can measure the amount of baryons in the universe very precisely. There's the odd and even peak shift differently, so that's a kind of characteristic signature. We can measure the amount of matter. So just by varying these parameters, and you can see the variations here, you basically see the effect. Decreasing the amount of matter increases the early ISW, so there's radiation driving, and that increases the power spectrum. So that's also a unique signature, and we can measure the matter density very well. The curvature we measure very well. The CMB basically measures the angular scale, and that, you can turn that into a measurement of the curvature of the universe, and you can see it's quite sensitive. Dark energy, however, is not, the CMB is not very sensitive to it, and small changes in dark energy only cause small changes in the microwave background spectrum. You could argue up down here, there's a large change, but there's cosmic variance down there. So you can actually trade off a change in dark energy with a change in the total, the curvature, for example. So that's difficult to measure from the primary anisotropy. In any case, with Planck, you can actually, so assuming the universe is flat, then there's a strong constraint on flatness, so the total density from, you can see just from this diagram, you basically get, these numbers for the major components in the universe: ordinary matter about 5%, dark matter about 27%, and dark energy about 69%. Okay, so the matter density and cosmological constant, these are the constraints. This assumes a flat universe, so this is kind of your base model. And so what the microwave background does is kind of set the big picture. It tells us how much of the cosmological constant we have in the universe, and it tells us how much of matter we have in the universe, or dark matter. And those are important, numbers that go into, if you're building a model, of dark matter, particle dark matter, this is an important number that goes in. Or if you're trying to, build up a model of dark energy, then the total energy content is also an important number. Right, if you try to relax that, there's a degeneracy between the curvature and the lambda, which is actually indicated here. Right, so that's basically because you're measuring the angular, from the peak acoustic peaks, you're measuring the angular diameter, and the angular diameter depends, on lambda, matter, and curvature. So you can actually break that internally. Previously, we would use other probes, for example, clusters or
supernova to say, there's something else in the universe. But you can actually now, we've made progress that we can actually break this. And so I haven't put it down here, but at project we made a first measurement of the CMB lensing and then turned that into a constraint on lambda just purely from the microwave background itself. So when you include CMB lensing, this is a secondary anisotropy. So now we're looking at an effect of something that affects the microwave photons on the way to us today. So we call it a secondary anisotropy. And that basically probes the late-time universe, and in particular, it probes the cosmological constant. Right? And so this is the degeneracy, and you can see that when you add lensing, it shrinks. So there's a zoom in of that here. So this is just the angular diameter degeneracy. When you add lensing, so you can't measure both lambda and matter or lambda and curvature together. Right? So just from the primary CMB. But if you go to a high L, there's more information from lensing, smoothing off the CMB peaks that shrinks this a little. Okay, my pointer is gone. Is there another pointer? Okay.
Last high-tech.
Oh, okay. Well, this is working, so. Yes. Right, so including lensing, which is a probe of the late-time universe and cosmological constant, allows you to shrink these contours, and you actually get some degeneracy breaking. The lensing here is reconstructed from the temperature field. Essentially, you need a 4-point function to reconstruct the lensing field. It creates non-Gaussianities in the temperature field, temperature map. Okay, and so if you add baryon acoustic oscillation data, you can shrink this even further. So, with late-time probes, so basically the take-home message here is the primary CMB is limited, and you either need to use secondary anisotropies from the CMB or other probes of the late-time universe to constrain dark energy. Right, so that's what I've said down here. And so this is again from Planck, and you see that now if you want to try to measure the dark energy, not just the amount of stuff in dark energy, but its equation of state. So just a constant equation of state becomes impossible with the microwave background. This is just Planck plus the WMAP polarization. And when you include the baryon acoustic oscillation, I think this is the Percival paper, Percival et al., you see that you get much stronger constraints. So the idea, I guess, observationally, the observational program is to try to shrink these contours as much as possible. And if you want to be more ambitious, you can also consider, the CPL parameterization, where you have a time-varying component to dark energy, the equation of state, W naught to WA, and again you see that the CMB is not very good. In fact, even adding BAO doesn't do very well, and so this is the current status where we are. Supernova does a bit better, but trying to measure time dependence of the equation of state at the moment is impossible. Right, so that will change with time as all these probes actually improve. Right, and so we need late time probes to strongly constrain the dark energy and its equation of state and the evolution of the equation of state. Okay, so what are observational probes with dark energy? So the four main ones, and there have been talks on the others in this conference. Type 1a supernova, baryon acoustic oscillations, cosmic shear, and the one I'm going to focus on here is galaxy cluster abundances. Right, and so this is a nice plot, a little old now, from Buchanan, that shows all these on the same graph, and this is now the equation of constant equation of state against the dark energy density. And the nice thing about this is you see that all these probes, and that's why each of them is being pursued individually, are complementary. And so combining them will give you, if they're all consistent, will give you a huge improvement or shrinkage in this, along these, or break these degeneracies. And clusters are down here. That's where basically this is from X-ray measurements. Okay, and when you combine them, you see you get a huge improvement in the equation of state. Okay, so I'm going to focus on galaxy cluster abundances, and as I'll say later, I'm mostly focused on a new tool to detect clusters, which is the Sunyaev-Zerdovich effect. But just to describe clusters and cluster abundances and how they work, how they probe dark energy. Right, so basically the cluster abundance is sensitive to cosmological parameters like the dark energy parameters by the evolution of the expansion rate and the growth function. So the expansion rate, so essentially what we're doing is we're just counting clusters and at a given redshift and critically above a given mass. Right, as we'll see, so that allows us to link the theory. As we'll see, the minimum mass is an important quantity, and understanding, actually defining a mass for a cluster is the crucial point in this whole exercise. Right, so weighing clusters is very important if you want to do cluster abundances. Okay, and I'll talk more about that. So we basically, the cluster abundance probes the effect of dark energy. Right, unlike other probes, it probes it through the Hubble, the smooth background model, so the Hubble expansion rate. So this is essentially the number of clusters in at a given in a redshift slice and in a given solid angle, right? And the volume element comes in, which depends on the Hubble parameter as a function of redshift, and the co-moving number density also comes in. Right? So it's just the volume times the number density gives you the total number, right? And so the co-moving number depends on the growth function. So the growth of structure also enters here. So the cluster abundance probe uses both the smooth background and the perturbations in the universe to constrain dark energy. And the matter power spectrum also enters in this function through the normalization, which we call sigma 8. Okay, so dark energy is probed via the smooth background and the perturbed universe. Okay, so how does it work? So just going into more detail, looking at these functions, right, and varying some parameters. Sorry, this is a busy slide. I hope you can see most of it. Basically, here what I'm doing is, this is from Hyman et al., 2001. So what we're doing is varying cosmological parameters. On the left, we're varying the matter density, and you see that, so I should say the way this is done is to keep the co-moving abundance constant today. Right, that's very well measured. So we normalize to the co-moving abundance today. What that does is, essentially that number translates into a constraint on the product of the matter density and sigma 8. Sigma 8 is the kind of RMS power on scales of 8 H inverse megaparsecs. And I'll say a little bit more about that in the next slide. So we normalize to the abundance today, and so what that means is, if this is a base model, which is omega matter of 0.3, okay, this is 10 years ago, so the Hubble parameter was 0.65, and W of -1. When you actually increase the matter density, right, you decrease, because of the normalization, that decreases sigma 8, and you actually get fewer clusters in the universe. Right, and I'll show you how that enters in the equation in the next slide. Decreasing the matter density increases sigma 8, and the number of clusters is extremely sensitive to sigma 8, so that increases the number of clusters significantly. Right? And you can see most of the cosmological dependence here is coming from the co-moving abundance, so that's sigma 8. The volume element doesn't change very much when you change the matter density, nor does the growth function. These green curves you can ignore, they're just some open models. And then on the right here, we changed the dark energy equation of state. So this is just a constant equation of state. And what you see is that the co-moving abundance changes, but there's also significant changes in the volume element and the growth function. So essentially, this drop here, so this is for an equation of state of W of -0.2, and the blue curve is W of -0.6. The green curve is again an open model. You can ignore that. So here you see the fall-off here is actually coming from a volume effect. So there's fewer clusters because the volume changes, and the volume is smaller, and the growth kicks in here. So the important point is that the matter density kind of raises the cluster abundance, at all redshifts, whereas the changing W, the equation of state of dark energy, right, has a different effect. So it reduces it at lower redshift and increases it at higher redshift. So if you can probe this whole redshift range here, you can break this potential degeneracy between the matter and W. Okay, so yeah, so I think I've basically said everything on there. So the cluster abundance, if you can go to a high enough redshift, so redshift kind of 1.5 to 2, it will become a useful way to break this degeneracy between the matter and W. And then sigma 8 is also an important parameter that enters. And essentially, the co-moving abundance, you integrate the mass function, so the number of clusters of a given mass m, and this is an important quantity. This is just an old fitting formula that was used in this paper, the Jenkins mass function. I just put it up here to show, there are more sophisticated versions of this today. I put it up here to show how the growth function enters. It enters in the exponent, as does sigma m, and that's on a mass scale m, and we're going to use sigma 8 to normalize that. So sigma 8 enters in the exponent, so as does the growth function. So the number, the co-moving abundance, is very sensitive to sigma 8. It scales as at this given mass as a high power of sigma 8. Okay, and so sigma 8 here is basically the amount of power in the large scale structure on a given scale. So we just smoothed it on a given scale R. So that's R would be 8 HM plus megaparsecs. Right, and so what you see is that the abundances are very sensitive to sigma 8. Okay, so the minimum mass is an important quantity here, and it's very crucial to characterize this properly depending on your survey. And to do this, you'd also need to understand what the cluster mass is. So measuring cluster masses is the whole key in this game, and I'll talk about it as I go along. Right, so what you see is that if you, this is assuming some fiducial SZ survey and Sunyaev-Zoldovich. I'll mention what the Sunyaev-Zoldovich effect is shortly. And this is an X-ray survey. So the X-rays you detect through Bremsstrahlung. The gas in cluster is very hot and emits thermally in X-rays. But the point of this plot here is to show that the equation of state actually changes the limiting mass significantly in X-ray surveys. So there's a cosmological dependence in the limiting mass. So for X-ray surveys, you really need to understand your limiting mass very well, because if you don't, then you could think that maybe there's a change in the equation of state when it's really coming from you're not understanding your limiting mass very well. Whereas for the Sunyaev-Zoldovich, there's a much weaker dependence on the equation of state, and you also see that the limiting mass is fairly constant. I'll mention that, I'll talk more about that when I talk about SZs, what the SZ effect is. Right, so there's a strong dependence in X-ray surveys, but not so strong in SZ surveys. And it's important because if you look at the formula again, this enters in this mass function, which basically is an exponential function of the mass. And so this minimum mass can change the number of clusters significantly if you get it slightly wrong. Right, so understanding the cluster selection function, which is basically what is your limiting mass as a function of redshift, is very critical in this game. Okay, so how do we, so now that we know how we can use clusters to probe or cluster abundances, counts of clusters, how do we find them, right? So traditionally, they were found in the early 1900s by using galaxy densities. So, optical, infrared, and other wavelengths we can measure galaxies. Nowadays we use weak lensing, X-rays, and I'll be focusing in this talk mostly on the Sunyaev-Zoldovich effect, which is a new method, in the last kind of 10 years, large surveys of clusters using the SZ effect. They were detected by the SZ effect that comes before. Okay, so what is the thermal Sunyaev-Zoldovich effect? Well, basically you have microwave background photons that inverse Compton scatter. This is a cluster, and you have energetic electrons, right, in the hot cluster gas. And so they basically, these photons gain energy from the electrons, and they get blue shifted. Right, so they scatter. So as the photon is traveling from the last scattering surface to us today, they pass through this cluster gas, they scatter, and they gain energy. So the total number, photon number is conserved, but what that means is low energy photons get scattered to high energies, and there's it's shown here. Right, so this is the black body spectrum of the CMB, and in the direction of the cluster you get a scattering, and the black body spectrum shifts. And the transition, the crossover frequency is about 220 gigahertz. Right, so here we see the difference between these two curves. So you actually get a dip, so you get less flux at lower than the crossover frequency and more flux at higher frequencies. Right, and so an SZ survey ideally would look for the decrement, what we call the decrement. Then the null, where there's no signal, and then the increment. Right, and here you see an example of a cluster in Planck. These are low frequencies. You see there's a decrement. Essentially, the cluster casts a shadow on the CMB. Right, and at 217 there's no signal, and then you get an increment here. Okay, so the clusters. This is a very unique way, a unique signature that allows you to pull out clusters from multi-frequency CMB maps. Okay, so the other point is that the signal that you actually measure, so this flux here, is basically proportional to the gas pressure integrated along the line of sight. So it's just n times t along. So in a given direction, you measure a y value, which is just this number here. So you're basically probing the pressure, which is n times t. And then when you integrate over the solid angle of the cluster, right, you get the total distortion, right, which is just the integral of the pressure. That's some measure of the thermal content of the cluster. Okay, from simulations, we've seen that we expect the signal, this total Compton parameter, to be tightly correlated with cluster mass. Right? Essentially, because it's n times t, X-rays go as n squared, so they are much more sensitive to changes in the number density. Also, if you have some process that changes the distribution of gas in a hydrostatic, kind of in a way that conserves or preserves hydrostatic equilibrium, then the pressure stays the same, and so you could move gas out. But for example, if you decrease the density but increase the temperatures in a way to keep this constant, then you actually the signal stays constant. So you expect the signal to be tightly correlated, and this is important because remember I said the whole game here is to understand or to measure masses, right? And so your proxy for the mass, right, as with other cluster surveys, in the X-rays you can use the X-ray luminosity or the X-ray temperature. Is going to be the strength of this method is going to be how tightly correlated is the actual mass of the cluster with your observable. Okay, so the other nice thing about the Sneddon-Zadovich effect is that it's a scattering effect, so it really doesn't matter where you put the cluster. You will basically get the same signal. There's a slight redshift dependence from the size of the cluster, right? It changes as you move it, to a higher redshift. Right, so it's a scattering effect, so there's a very weak redshift dependence which comes in through the size. Right, and this means that you've got a very simple or simpler selection function, and that explains why if you looked at the limiting mass as a function of redshift, y was fairly constant. Okay, because there's no dimming, right, as you move the cluster away, right, because it's a scattering effect. Right, so what you hope is that you can find all clusters in the universe about a mass limit. So the mass limit is going to correspond to the flux limit in some sense, right? So so the noise level basically sets the flux limit, and that will give you or sets the minimum flux of a cluster that you can measure, and that gives you a mass limit. Okay, and so what we see here, this is actual data from the Atacama Cosmology Telescope, the project I'm involved in. I'll talk a little bit more about that soon. So this is a sample of just 15 clusters that we used for the cosmological constraints that I'll show later. And this is the full sample of clusters. The reason we use fewer is because we have follow-up observations of these clusters. And you see that if you fold in all the selection function of the survey, which you can model, you basically get this dash curve, and it represents very well. So these clusters are found by setting a certain signal to noise threshold. in your maps. I'll describe that shortly. And you see that they agree reasonably well. Okay, so we can, there is hope that we understand these, the selection function of these SZ surveys, these SZ surveys. Okay, so what experiments or instruments are being used? Right, so there's Planck satellite that did an all-sky survey of clusters. There's the South Pole telescope, which is down in the South Pole, which is it's the driest place on Earth, and the other very dry place on Earth is the Atacama Desert. So this is 5,200 meters up in the above sea level. So it's very high and dry. Right. So to enable these surveys, what you really need is you need to scan large areas, so thousands of square degrees, to detect lots of clusters. You need high resolution, so the typical size of a cluster is a few arcminutes. So you need something of arcminute resolution, right? And that pushes you to something to larger telescopes, right? And or larger primary dishes. And you need high sensitivity, so you need lots of detectors, and technological advances have allowed all these things. In this talk, I'll focus on ACT, but we'll also look at results from SPT and Planck. Okay, so the higher resolution allows you to basically, so in these SZ cluster surveys, if you go to higher resolution, you basically can find high redshift clusters. And what I'm showing here, firstly, let me say this is the sample of ACT clusters that we found. There's about 68 here. And this is the mass of the cluster against the redshift of the cluster. And so you can see we're finding kind of clusters at 4 times 10 to the 40 M500, uniformly in redshift. Okay, whereas here, I guess with Planck, these black circles are the Planck clusters, and you can this is reminiscent of some kind of flux cut. So, the reason actually is because as you go to higher redshift, the Planck beam is much larger than the ACT or SPT beams, and so you basically resolve out your cluster. So, you have beam dilution, and you don't detect the cluster. So Planck is good at measuring low redshift clusters, which are large in size, and so these are the ACT and SPT points, clusters that you detect, and you can kind of see that we're basically detecting clusters above a certain mass that's roughly constant in redshift. Okay, so that gives you hope that you can understand your selection function reasonably well. Okay, so the beauty of, and just to emphasize the point I made, the beauty of these high resolution, so arcminute resolution, high sensitivity experiments is that you can do things. So this is a patch of the sky as seen by WMAP, and you see with the high angular resolution of Planck, you can start to probe in a smaller scale CMB features, and then with ACT, which has even higher resolution, about 5 times better, you basically can see the same CMB, so that's reassuring. You see the same structures in all the maps. But also you can start to pick up these dusty galaxies at high redshift. So these are these dusty star-forming galaxies. And you also start to pick up, as I mentioned, this is at 148 gigahertz. So below the null, you see a decromatia, and this actually corresponds to a cluster. So you can actually see things popping up, and that's the beauty of the higher resolution. Okay. Okay, so I'll just go quickly through this. So this is the ACT telescope. It's a project that I'm involved in, and a number of other people at UKZN. So we're a partner in the project. It's located in the Atacama Desert in Chile. So this is the telescope. It's a 6-meter primary, and it's an off-axis Gregorian. There's 3 frequencies we've measured with ACT, 148, 220, and 280. So these straddle the null. That corresponds to 2, 1.4, and 1 millimeter. And we basically got arcminute resolution in these bands. This is the view, and we basically scan back and forth. We then swap over and scan. That allows us to cross-link, and that's important. The modulation, the scanning back and forth is important to remove, basically contaminants. So you basically modulate them out, and then when this field comes over, we scan and we we cross-link, and so that allows us to remove, if you know, these detectors are unstable and they have one of the F noise, so we can actually remove that by doing the cross-linking. And so there's 1,000 of these. So it's kind of like a, a camera. So there's 1,000 detectors here. And so, these advances have allowed us to make these high sensitivity maps. Okay, so the ACT kind of spent 3 seasons observing, and the data that we'll focus on here is in Stripe 82. This is the Sloan Digital Sky Survey, Stripe 82. And so I'll mostly talk about that. But we've also scanned in the south where we overlap with SVT. We've also found clusters in these regions. Okay, so how do you detect clusters? Well, so this is the original map. So once you have the time order data, you have to use a lot of intensive computing power to convert that time order data into maps. Once you do that, you start to see features that are CMB-like, or this is a cluster, and this actually turns out to be a dusty galaxy. To be more convinced, you actually filter these maps, right? And I'll describe the filter next. And out pops out a cluster and a dusty galaxy source. So this is a match filter that we use to extract the sources. And this is what it looks like. So here's the ACT beam, the dotted line, what the cluster would look like, the cluster template, the profile of the cluster, a spatial profile. And this is the filter we use. The negative here is basically to remove the microwave background, which has a lot of power, even on scales approaching the cluster. So this basically cancels the large scale signal. And when you do that and apply this filter to the maps, these dark spots start popping out. So the clusters just come up at various levels of signal to noise. And then you go and look. And the beauty about this is because we have Stripe 82 data, we're in Stripe 82, you can go and look at the Sloan data at this position, out pops the cluster. Right? So this is J0223. Right? And so you can go to S Sloan and confirm it. Right? So optical follow-up is crucial to confirm the kind of purity of our sample. Okay, so this is the sample. So these are all, this is the Stripe 82 stripe, and these are the various cluster detections we've made. Some that actually we go beyond Stripe 82. Right, so we've got about 504 square degrees. The median redshift of clusters we detect is about redshift 0.5, so much higher redshifts. And we've detected 68 clusters in this area, and 19 of these are new, so at higher redshifts. The others were previously detected either in X-rays or in in optical. And so here's some of the clusters. And you can see, these are some of these are Bell clusters, and they also have ROSAT. This is the biggest one in the equatorial, most massive, 2327. Okay, so we've got these clusters, and so this is just showing you again. This is the sample and comparing it to Planck. So now that we've got the clusters, the important thing is to get the mass for these clusters. And this is the hard part. What we've chosen to do is to calibrate this Y-M scaling relation, or basically use the simulations of the SZ signal in clusters versus their mass. Right, and we've put in different simulations. We've got a simulation which is just a pure adiabatic simulation, and in fact, this is called this universal pressure profile, which is the RNO profile, for those of you who know what that is. So that's one of our models. Then we have another model where we have feedback from AGN and supernova, and some non-thermal pressure, and then we have a third model where we have significant non-thermal pressure. These basically decrease the SZ signal, right, because they throw out gas or push out gas from R500, for example. And so this normalization of the SZ, this is a proxy we use for the SZ signal, and this is the mass of the cluster. And so this normalization, goes down if you have less gas in the cluster. Right. So we use these models, but then later we also calibrate these models because we've measured dynamical masses, so using velocity dispersions from velocity dispersions of clusters by basically measuring the redshifts of the galaxies in the cluster. And the other useful point, okay, let me speed up a bit, is that we've compared to SPT and their masses. They have a completely different method of measuring mass, and we actually agree, our V12 masses agree reasonably well with their masses. And that's a completely different data set with completely different analysis method and ways of characterizing the mass. Okay, so what we find is, so now we can go to the cosmological constraints. We have a full likelihood, etc., that the data goes into. And what we see is, what we chose to do was to fix our scaling relation, not let it vary, but to explore the systematic effect from not knowing the scaling relation. We plotted these three models. And so here you can see this area is basically telling you what the systematic effect is. So here's the non-thermal, the V12, and the unknown or universal pressure profile. And the spread in this region is basically telling you, what the systematic effect is from not knowing the scaling relation. And so we basically use 15 clusters. So the point I'll make is that we're going to go to much larger cluster surveys, and we will get these error bars or these region contours will shrink. Okay, and then this is the WMAP measurement, which is orthogonal, as I showed you in the previous plot. I'm plotting sigma 8 against omega matter. And so these are our constraints. So at the moment, the message is we're really limited, but mostly by systematics and trying to constrain the scaling relation, but also we can improve in our sensitivity. And this is just, if you include the dynamical masses that we measure for these clusters and calibrate the scaling relation. So this is the way to go. We need external constraints to calibrate our masses. This is basically what you get, this region here. And then if you combine the WMAP, you see that the error bar shrinks slightly, but not significantly. So there's more improvement. And then, that's just a zoom in of that region. And so comparison to other measurements, so comparing sigma 8, which is an important parameter we measure. I'll talk about W now, or next. This is, there's this tension, and I guess we're going to wait to see what the Planck results are, coming out next month to see what happens. This is sigma 8 derived from the Planck CMB power spectrum, whereas this is the Planck clusters, and there's some tension between them. So this value is kind of everyone's trying to chase down. Our dynamical masses put us up here, but we've got a bias in that we need to put in for converting from velocities to mass. And if we use this new updated model, we get lower masses, so this number will come down. So this is something interesting to watch, in the near future. And so what about W? We really don't, make significant constraints on W. The parameter space is quite large, so we need better, as I mentioned, better calibration and better statistics. So more clusters, right, which we're basically accumulating. And if you put the dynamical masses in, the previous plot was without the dynamical masses. If you put those in, you actually see that we do shrink the WMAP plus supernova region, but not significantly, just slightly. SPT have more clusters, and so this is the ACT plot, and there is the SPT plot, slightly older constraints. And you see that if you add clusters to CMB plus BAO plus supernova constraints, which is the gray region, you actually do gain there. So, clusters will be very useful in this whole exercise. And so, as I mentioned, the important thing is that we, two things. One is we need more clusters. So we have larger surveys coming online for clusters. And secondly, we need to calibrate the mass YM relation. Okay, and so we've been doing some work here in South Africa. We use dynamical masses. This was mostly on DLT and Gemini. But we're doing some work on salt here, so I'm just going to speak about this quickly. We've observed 7 ACT clusters. So this is now from the expanded equatorial sample, the full 68. We only used about 20 of those for the cosmological constraints. So we've observed them with the Roberts-Stobie spectrograph from salt. So this paper has been submitted. So here's an example of one of the clusters we detect, and the spectra of the member galaxies. And so and so you convert those spectra into redshifts, and you get velocity dispersion from them. and then you get a dynamical mass. And so this is using the old scaling relation between mass and velocity dispersion, and these are the constraints you get. So they're a bit scattered, and this is if you use the new scaling relation. So anyway, these clusters will go into the full sample and inform the scaling relation constraints. Right, so that's one important part of the exercise, and so we'll continue to do this work on salt, following up clusters we detect. Okay, so just a summary. I think I've got a minute to that. As that cluster surveys are producing, starting to produce, even though they're relatively new, they're starting to produce interesting cosmological constraints. The main challenge is the calibration of the Y-M scaling relation, and secondly, we need more clusters. The follow-up of ACT data, basically we've got dynamical mass measurements for most of the equatorial clusters. The 7 clusters I showed you with salt will go into that set. So we can do a larger study, with a full sample of 68 clusters. Right? But it's important that we have masses so that we can constrain the scaling relation. We've also got an ongoing program of following up these clusters using weak lensing, X-rays, high resolution snares or low wave in the optical and infrared. So there's a large multi-wavelength program, as I mentioned out here, and you need this coordinated multi-wavelength campaign to derive the masses, and that way limit your systematic uncertainty. Right, in terms of getting more clusters, larger SZ surveys are coming online. So ACT and SPT have second generation instruments on them. So ACT has a polarized polarimeter now, and so does SPT. So they're basically measuring the polarized microwave background, and that's useful for lensing and other things. But they'll also find lots of clusters. Both these projects are going to do large cluster surveys, and the third generation of these experiments, SPT 3G and Advanced ACT, have both been funded, and going to have significantly more sensitivity and sky area that they will cover. So we're expecting thousands, 10,000 of clusters from these surveys. They're going to cover basically the whole southern sky. Okay, so there's a lot to look forward to, and I've mentioned the results from other probes of clusters, X-rays, etc. But the main point here is that the SZ is kind of promising.
Thank you very much. Time for questions.
We have different masks. We have the M500, we have the dynamical mask, and then you have the mask which goes into the theoretical prediction.
So we use
what do you use for the theoretical prediction?
So we convert the theory to M500. So everything is done in M500. Oh yes. So I didn't go into the details, but we basically use the R0 profile, and if we have a different simulation which has feedback, etc., then we have a kind of a form factor which converts, and that just changes the normalization of the scaling relation. So I can describe it in more detail too, but it's we basically use a universal profile to measure the SZ flux, but then convert that depending on what model we basically use. Yeah, so the dynamical mass we convert. So we've been doing simulations to try to calibrate the plus M500 or M200 to dynamical masses. And so via simulations again, we try to calibrate that relation. And that's actually what has pushed us into moving into this Munari scaling relation, which our simulations confirm.
I wanted to know, is there any instrumental limitation why there are no higher clusters? Because there were no there. Why the survey is scaled at 1?
Oh, no, we actually detect clusters beyond that. So I think the highest SD cluster detected now is about 1.4 or 1.5. So it's just a case of, are there clusters there? And have we covered enough area? Then they need to be massive enough for us to see that. They have to have a certain SZ flux. And so are there massive enough clusters that are high enough redshift for us to see? And have we covered enough sky area? And so the highest redshift cluster is about 1.5.